Hi, let's start with a brief summary. In the previous two videos we introduced the concepts of an eigenvalue, an eigenvector and an eigenspace of a square matrix A. Given an n by n matrix A, we have seen how to check whether a given vector is an eigenvector of A. How to check whether a given number is an eigenvalue of A. How to determine the eigenspace for a given eigenvalue of A. There's one important question that we have not addressed so far, which is, how can we find all eigenvalues of a given n by n matrix A? We'll find an answer to this question by stringing together several equivalent statements. Here we go. In the previous video, we have seen that a number lambda is an eigenvalue of a matrix A if and only if there exists a non-zero vector x such that A minus lambda times I times x is equal to the zero vector. This, in turn, is equivalent to the statement the square matrix A minus lambda times I is not invertible. Leaving out the statement in the middle, we thus can say this. A number lambda is an eigenvalue of a matrix A if and only if the matrix A minus lambda times I is not invertible. Recall from the theory of determinants that A minus lambda times I is not invertible if and only if the determinant of A minus lambda times I is equal to 0. Leaving out the statement in the middle again, we thus can say this. A number lambda is an eigenvalue of a matrix A if and only if the determinant of the matrix A minus lambda times I is equal to 0. The equation determinant of A minus lambda times I is equal to 0 is called the characteristic equation of the matrix A. It turns out that the left-hand side of this equation is a polynomial function of lambda. This polynomial is called the characteristic polynomial of A. So we know that the eigenvalues of a matrix A are the solutions of the equation determinant of A minus lambda times I is equal to 0, which is called the characteristic equation of A. Let's have a look at an example. Consider the 2 by 2 matrix shown here. The matrix A minus lambda times I is obtained by subtracting lambda from the entries on the diagonal. The determinant of this matrix is equal to 1 minus lambda times minus 4 minus lambda plus 6, which is equal to lambda squared plus 3 times lambda plus 2. This factorizes into lambda plus 1 times lambda plus 2. Hence, the solutions of the characteristic equation of A, which are the eigenvalues of A, are equal to minus 1 and minus 2. The characteristic equation of the matrix in this example turned out to be a quadratic equation. This is true for any 2 by 2 matrix. What about 3 by 3 matrices? Let's have a look at the example shown here. The determinant of A minus lambda times I can be calculated by expansion along a row or a column. Expansion along the first column yields the sum of the 3 expressions shown here. After performing the required calculations, you will find this expression to be equal to the third degree polynomial shown here. The eigenvalues of the matrix A are the roots of this polynomial. In general, it is not easy to solve a third degree equation. In this particular case, the polynomial happens to have the factorization shown here, so we can conclude that the eigenvalues of A are equal to minus 3, 2 and 3. The characteristic equation of the matrix in this example turned out to be a third degree equation. This is true for any 3 by 3 matrix. The following theorem probably won't come as a surprise to you. For every n by n matrix A, the characteristic polynomial, determinant of A minus lambda times I, is a polynomial of degree n. This is an important theorem in the theory of eigenvalues. Using the fundamental theorem of algebra, we can immediately derive from this that every n by n matrix has n eigenvalues, with the usual side notes shown between brackets. The characteristic equation is an nth degree equation, which in general is not easy to solve for n larger than 2. Fortunately, several numerical methods exist that can be used to calculate good approximations of the eigenvalues of a matrix.